There we go. All right. Welcome, everybody. Happy New Year. We are this sunny, warm day in Pittsburgh today, and we're very happy to have the speaker come all the way from a very sunny and warm place. And I'll introduce Dr. Juan Santos, who's going to introduce the speaker.
Thank you. And then I will introduce Costa to introduce Kali. So welcome to the first CS Collegium, and it gives me great pleasure to welcome Dr. Constantinos Costas back to Pittsburgh, and specifically in our department. As some of you remember, Costas was actually an assistant research professor here for 3 years. And I have to admit that it's my fault that he spent 3 years in the cold space after he graduated from the University of Cyprus. I know him since he was a master's student. And then as part of his PhD, I was asked to be a part of the external examining committee that to defend his PhD. There is completely different than here. Usually you bring people outside the department and outside the university to examine the candidates. And I was one of the examiners. And needless to say, I was so impressed about his work. So I recruited him to come to Pittsburgh. So that is giving me great pleasure to, again, as I said, to welcome him. I failed to keep him around. I have to admit this, because here in Cyprus, sunny weather and other significant others was a big attraction that led him to, when I say significant others, I'm referring to his company. Okay. Don't get it wrong. Just, so, and when he went back to Cyprus, he put his big plan into work. His heart has always been to start his own company and contributing to innovation through research and applied computing. So he founded this Rinnoco company that he has been successful in the last 2 years to get 4, I believe, European co-founding projects. And I guess he's going to give us a talk about these projects. And hopefully you won't forget our collaboration. So welcome.
Thank you so much. As Panos said, I'm going to go over the tools, the research that we are doing, and I will give you the inspiration of this work and my company as well. So first of all, I want to discuss a little bit about what is my company doing. We're trying to do research, innovation, and other services. The company focusing on data storage and data management in a more low level that I'm going to show you. And of course, it was founded by me in 2021, but it was active in 2023. So yes, it's been 2 years that we're active. The whole idea is to build these tools for big data. It was an inspiration from my PhD, and I'm going to show you some work from my PhD. And then we're going to discuss about the new tools that we are developing. Of course, I'm a researcher, so we have many collaborations with many universities, including University of Pittsburgh with the Alien Lab, Brian Vasilis. And we are planning to create a platform for efficient storage. But right now we are building 2 tools. One is the signature-based conversion tool, and the other one is a data decay tool. And then we want to build the tools, integrate those tools into a platform, and then have a platform as a service product. So I will start with the brief introduction. I will go over the inspiration, as we said, with the spade, discuss the first tool that we are building, the spatial and compass tool, we're going to discuss the data construction idea, then go to our collaborative work with IDT, the decay pipeline, and then I'm going to conclude the presentation and answer any questions that you may have. So, one of the biggest motivations for my work is the big data applications. As you know, we have a ton of social media platforms. They are using the data for specific cases. For example, Facebook is using the data for finding the user personalization and ad targeting. You have Twitter with trend analysis, Amazon with product recommendation. You have Netflix for movie recommendation, and you have Spotify for music recommendation. Also, we have some other big data applications. Google, of course. I'm pretty sure that you know Google. So search engine is keeping a lot of data, personalized data. We have Uber and Airbnb for route recommendation or pricing and demand forecasting. And those can be categorized in these three categories: social, spatiotemporal, and spatial data. Now, because we are talking about big data, we need to define this big data. You may hear the 3 Bs or the 5 Bs. In our case, we are going to stay only on the 3 Bs. The volume can be from terabytes to petabytes. Then you have the data model, the variety of the data can be structured as in a database, a relational database. We have semi-structured as in JSON file or JSON data. And then we have totally structured data, web, and logging. And the last V is the velocity. How quickly the data are growing. Of course, you can say that big data is data that does not fit in Excel, right? But just to be formal, big data is data that are large enough that are stressing our computational resources, either in storage or in processing. In our case, we are focusing more in the storage aspect, but as a side effect, we have processing benefits. So let's talk about data storage. IDC said that the data are growing 19.2% every year. So we are going to reach 394 zettabytes by 2028. So just to give you the idea of how much is this amount of data, you can think that if we get these 394 zettabytes and store them in Blu-ray discs, if you are young enough, you don't know this, this is a Blu-ray disc. You can store them and you can go to the moon 49 times. Or if you think about something else, about the Earth, you can go around the Earth 472 times. Okay, so a ton of data. Now, what are the problems? What are the challenges? We have the data. So you can imagine that organizations are collecting data. We saw Google earlier, we saw Uber, Twitter, Facebook. It's collecting data. But the problem is that there is a ton of data, a ton of case stacks. So they have the problem that they don't know what are they looking for. So they need to find the needles in a field of case stacks. And of course, they're going to get a data scientist. Okay, this guy here. But if you think about this, you have a ton of data, you need to process them, store them in a quick way, you need to retrieve them, you need to find what you are looking for very quickly. So the most important part is to figure out which part of this data is going to be useful for the application. The next thing is about transforming the actual data. So by getting raw data, we need to give the data in a specific way. And the last thing is about storage and transfer. So just again, to give you the pointers of what we are doing, we saw the trend that the storage is getting cheaper in a much less rate than the processing power, which means at a point, and actually this is the point here, because we have AI, we're getting data, we want to store it. So it's getting very expensive. Of course, I'm pretty sure that all of you know some solutions. One is machine learning. You can analyze the data, you can figure out what data you want, you can identify patterns, you can do prediction, you can do a lot of stuff with data. But remember that this is a huge amount of data. So you need to figure out what data you want in order to do the machine learning part. Then, of course, we have this idea of data visualization. For example, if we are looking for a specific part of data, there are techniques that represent the data in a different way, in a more intuitive way, so you can find the data that you are looking for. Of course, the next part is processing the data. There are architectures that are using distributed computing in order to split the data, do the processing very quick. And the last thing is what we are working on, the data management and the conversion schemes for the data. Of course, we want to minimize or reduce the size of the data. And also, we want to satisfy the space requirements for either a specific organization or for an individual that is trying to figure out what to do with the data. The last thing is about a new idea, the data decay. Unfortunately, Brian left. So we're working with a team on this. The idea is that we can remove data, but keep the information of the data in our system. And we're going to discuss this. So just, again, to give you the big idea, you have a big data architecture. Always you need these layers. You want the storage and indexing part. Most of the system nowadays, they're using a distributed file system, and most of them are using HDFS. The next layer is about the operators. You need to transform the data, as we already said. There is this processing system that allows you to have the traditional operators in a distributed way. And of course, you want to do something with this data. You want to provide some applications, see some reports, give some aggregated results for people to use. So I will show you now Spade. Spade is a complete platform that is using what we already discussed. It was made for a telecommunication company back in Cyprus. So we have access to real data. For this demo, we anonymized the data, so don't worry about this. Actually, you can track, you can do SQL queries directly on a distributed system. In this case, we use Hive on top of Spark and Spark on top of HDFS. Actually, this was a great tool for the operators in the telecommunication company to figure out call drops, figure out the quality of the network, and understand what is happening in general with the network. So going to this direction of telco data, typically the telco operators are doing accounting and billing sessions based on the data they have. But if you actually see the value behind this, you can do a lot of interesting applications. You can do churn prediction, you can do optimizations of the network, you can assess the quality of the service, and even traffic map. So why these data are so big? These data generally are generated on the cell towers and are generated every second. So we are keeping statistics of signal strength, call drops, value of measurements, and this is coming up to 5 terabytes per day for a 10 million clientele, which means 2 petabytes per year. Okay. So again, a ton of data. If we want to keep this data in order to do either machine learning or any other application, we need to store the data, correct? Okay, so one way to store the data is to apply compression and then store the data. I'm pretty sure that you know compression. The idea is that we're encoding the data with fewer bits than the original representation. The compression allows us to shift the load from storage and network I/O to processing I/O. Remember what we said before, the processing power is getting cheaper than the actual storage. So it's more important to move the load from storage and network to CPU. So yes, with the compression, we can save enormous amount of data. And if the data is smaller, the IOs are less. So it's a side effect, again, on the processing and the response time of the system. So the goal here was, given this setting of this telco data or spatial big data coming into the system in batches, in 30-minute batches, for example, we want to minimize the storage, but also minimize the response time. So I will give you directly the results. So we anonymized this dataset, the dataset that I showed earlier. It was consist of 1 week of measurements, 1.7 million call detail records, 21 million network measurement records, and the telecommunication company had 300,000 users. So the first thing that we wanted to see before running anything or evaluating anything, it was if there is a potential for the compression ratio. So if we compress the data, are we going to get anything back? So we ran Shannon's entropy. We saw that a lot of attributes had an entropy 0 or very close to 0, which means that these values are not changing a lot, which means that the compression is going to be very effective. So when we run this, actually, I will show you the experiments up there. So the next thing that we wanted to explore is the decay. So we saw the compression, we saw that there is a potential there. We wanted to evaluate the system, but also at a point we said, okay, we are compressing data, we're putting the data into the storage, okay, the next batch, the next batch, the next batch. When are we going to remove data? So the question was, okay, we want to alleviate the stress of the storage by using a different kind of technique. That was the data decay. So as a fruit is rotting away and it's disappearing, the same one we want to apply to the data. We want to gradually remove the data until we have no data at all, but we want to keep the information. Okay. So this idea was presented back in 2015. CIDR was having different techniques or different ordering of decay. And the benefits are saving a ton of storage while keeping the exploration capabilities the same as before. And we're going to discuss how to achieve this. Also, there was a different definition of deep schema decay from Professor Stonebreaker, but this is not related. So let's start from the system that we showed earlier. We use conversion, we're using data and decay. So the idea is that we have this temporal resolution or index resolution, and then every time that batch is coming, we are compressing the batch and putting the rightmost part. Now, if you notice this is a Foster-like structure. So as we said at the beginning, we want distributed systems, we want to partition the data in a way. So we want to match the partitioning of the data in the file system to the higher level. So for each one of these batches, we are putting the batch under the correct year, month, and day. And then we wanted to keep a high level information about the lower level data. So we have this increment module, the highlight module that we had a materialized view for each level. So this is important because we said before, we want to remove some data, but also keep the information. So the first idea of the data decay was remove the oldest individual. So remove the data that are very old. But because we had these highlights, we could answer predefined queries. And this is with an asterisk. We have only some queries that we wanted to answer, but we wanted to remove some of the data. So that was the first idea of the data decay.
So by materialized views, you mean aggregation?
Yes.
You aggregate the data and then removing the details.
Correct. So this is aggregation of the lowest level, and this is aggregation from this level. This is aggregation from this. So you have a multi-level access to this visual, interesting data, for example. Yeah. Okay. So
progressive loss of accuracy.
correct. We're going to come to this. Okay. So yes, when you are removing information or removing data, you are losing information. Okay. So we are keeping only the interesting information or the required information. Okay. So I wanted to show you very quickly the experiment just to see how fast or how efficient was our system. We compare it to a raw system. We are storing everything in a raw format. We have tracked the state of the art at that point and our own platform. And we wanted to see we are very focused on seeing the time and the space. So we ran this over a testbed. I'm not going over the details of the testbed, but I want to show you this. So we have this set of data. The ingestion is on the left, and the space on the right. The ingestion is how much time do we need to put the data into the system, and the space is the space on the disk. So if you notice here, it is the worst case here. we are losing some speed in ingesting the data, but we're gaining a ton of space. So we are a bit slower, but we're getting 1 order of magnitude less space. Of course, we are going to say, yes, we are removing data. It makes sense, right? So the most important thing is to understand why this part of the data was removed. And actually, here we have only the compression part. Okay, we don't apply any data. So the data decay part, it's a very interesting thing to consider, and we are going to discuss it later. But the results are only for compression. So getting a badge, putting the rightmost path in a compressed manner, we're getting 1 order of magnitude less space. And this is expected because we are compressing data, right? Okay. So
just include also the aggregations.
yes,
So the tree.
yes. So the whole idea is that we have this big tree. We are doing the aggregations, we are doing the compression, we are storing everything. And this was first of all.
Battery.
No, I think it's the project.
So why don't we fix that Costa?
Yeah.
Did you look at how much you're saving by deleting and how much you're adding by
Compression. Yeah, I have the results. We're going to discuss it. But yeah, this is very interesting. Thank you, Vic. So we're going to see first the compression part, and then we're going to see the decay, and then we are going to see some covariates. So the idea for the compression was very interesting for us.
So the question that was before, when you have these savings,
Yeah.
do these savings of order of magnitude consider the trade-off of the cost for the aggregation? I think this is what
Yes.
I believe we are.
Yeah. At this point, we are doing the aggregation, we are doing the conversion, and the indexing as well.
So both time and storage include the aggregation.
Yes,
Is the
correct.
final-
Absolutely correct. Yeah. So at the next step, we want to see a more, let's say, sophisticated solution about the compression. We are not going to create a new compression algorithm, but we are focusing on applying the best compression possible to a specific set of data based on the data characteristics. So the idea of the spatial, which was the first version of our tool, the first prototype, let's say, was to find which compression can achieve the best space based on the data characteristics. So the data characteristics are a bit loose term that we are going to discuss again, but it was to identify which compression scheme can apply to a specific part of data. So the first idea was to get the data sets, check again if the data sets have this potential of using compression schemes very efficiently. We saw that there are a lot of attributes with 0 Shannon's entropy or close to 0. And then was the first version of our idea. So go over the data, discover the columns that are similar based on the entropy and on a threshold, which empirically was set to 0.3. But the idea was to find the data, similar types of data, similar characteristics, put them together. At this point, we had only 2 groups of data. So the data that are very similar and the rest of the data. And then we applied the best compression scheme that we that we could have. And at this point, the only thing that we could do is to run everything and choose the best. The idea, of course, was not that, was to create a knowledge base or something that will allow us to find the best compression scheme without running out. Okay, so the idea, find the columns, put them together, and then do a different compression to these columns, if it's necessary. At this point, only 2 groups. So we ran some experiments, wanted to see if there is potential to run this. We have a set of algorithms from the zip file library, gzip, bzip, and LZMA. And then we compare that with an approach that compressed the whole data set with only one compression scheme. We have the idea of grouping the columns, but then apply the same compression scheme. And the final version, which was, let's do the groups, apply the best compression scheme for every group. So this was our data sets, 20 gigabytes and some more complex data set, which was less than a gigabyte. And then we wanted to see the results. So the first result was about 4%. Okay, 4% improvement with only doing 2 groups and apply the best compression that you can apply to these groups. Now you're going to say, yes, 4% is nothing. I totally agree, but we saw the potential. So we put some numbers down and we said, okay, let's see how much is this 4%. So if you do the calculations for the 4%, it's about for Dropbox with 17.75 million paying users who are paying $10 per month, and you are saving 40 cents per month, then you are getting up to 7.1 million per month savings, only with this approach. We are splitting the data, applying the best compression scheme, and we are saving a ton of data. Of course, you are going to say there is more in the Dropbox service. Yes, I totally agree. But this is about the potential. We saw that there is potential in this specific product. So we continue with the investigation of this direction. Actually, now we're working Compass, which is, yeah, okay, sorry.
Just a quick question. So in this, we are talking just about the lossless compression, right?
Yes.
There is no decay.
No, there is clean compression, only gzip, bzip, and LZMA, lossless compression, yes. Okay, so 100% accuracy. Okay, now we said there is potential, so let's move on and try to do something more sophisticated, some more research about it, and figure out what to do. So the idea was very similar with this example. We have a wardrobe that adapts to the weather and activities, and we have Compass that's going to adapt to different characteristics of data. Okay, so imagine that you are in Cyprus. Okay, Cyprus is very sunny. So what you are going to do, you are going to wear t-shirts, shorts, and slippers.
Site is here also, but
Yes, inside. This is outside. Okay. So if you have a different weather, of course, let's say rainy weather, you want to wear something different. You want to wear a light jacket, maybe shoes, maybe have an umbrella, because it's raining, right? And then if you have a snowy weather, like here, okay, you want to wear different clothes. You may have to wear gloves, a scarf, maybe a hat, or a warm jacket, some boots. So as you can see, there is an adaptation of the weather with the clothes that you are wearing. Okay. So the idea was, let's describe this as sunny data, raining data, snowy data, and then we can apply the best performing compression algorithm. This is only for example here, but we can identify that there are different characteristics, and then apply the best compression algorithm. So you can imagine that sunny data is data that are simple, and we can use a simple and fast compression, less complex. Then you are going to the rainy data, moderate complex, and then you are going to the snowy data that are very complex and large. So you need something. So the idea was to give a characterization of the data, understand what are the data. So the idea of the compass now was to find the columns, then identify the features, the characteristics of the data, and then group the data together. Okay. To a different number of clusters. Remember that Zivago was only 2 clusters, split 2, and then apply the best compression algorithm. In this case, we are doing a k-means clustering, and we can find a ton of clusters. The number of clusters is a question mark for now, but we are going to discuss it. And then, because we found the columns that are very similar to each other, put them together in cluster, we can apply the best compression algorithm, and then put them back to the storage. So just to give you the whole idea, we have this phase of a setup. The first thing is to read the data from the database, then cluster the columns of this database based on one of the following. All the data points, the actual data, on the entropy that we found that it was very useful, and also these features that we need to discuss, because right now you can do that. You cannot do that. Okay, the next step is to test everything, all the possible combinations, all the number of clusters, all the compression algorithms, find the best one, keep the results, because we want to create this knowledge base, as I said, but it's a more of an assisted, let's say, storing tool. Okay, so we are saving the results. We know for a set of data, the best compression scheme. So in action, what we are doing, we know these results, so we can build a specific model, most likely a decision tree. And then based on that, we can identify the best number of clusters, the best features that we can use from the data, and the best compression algorithm. So we can apply the clustering, we can apply the best compression algorithm, and then store the data back to the database. Unfortunately, I don't have results, but I have the results somewhere. If you remember before, we had 4%. In this case, we had 56. So 56% is a huge number. Okay. So there is potential. The project is not finished yet, so we need to do more. And I'm going to send you the results. Okay. Okay. So the next step. Yep. Okay. Yeah. Go ahead.
I was just gonna ask.
Yeah.
56%. So you have the storage, but here you're trying all the combinations and
Correct.
this one. So what will be time processing stuff also compared to this?
Perfect. So this is a very good question. there is this phase of testing all the possible combinations. It's very costly. Okay, 100%. It's very costly. But the idea is that we are going to build this knowledge base, which is trained over different data sets. And we're going to match the features, the characteristics of the data. So, for example, we can match the entropy. And if we know that the entropy is around 0%, you need to use this specific compression scheme. So yes, there is a huge trade-off here, but at a point, we hope that we are going to manage to keep this decision tree model in a way that it can adapt to different data sets. So at a point, if we test a lot, we are going to remove this step and have only the second step, which have the statistics, have the conversion algorithms, and choose without testing everything, the best compression scheme.
Did you try to use the worst compression scheme?
No.
Just to see how.
Actually, I ran everything, so I know, yeah, but I didn't check. So yeah, maybe we can do that. Actually, we did something different. I don't have the result. I need the result to show. Yeah.
So how frequently do you need to perform this? Because you say every day you have a lot of new data byte.
Correct.
Frequently perform the Python is used like all
Yeah, perfect. So again, this is a great question. When you have new data, you need either to do the setup, or if it's in a specific setting where you have, for example, on the telco data, the pattern was the same. So you had to run this only once. And the features and the columns are going to be the same. So for one column, we are going to use always this conversion scheme. It depends on the setup. If the values in the columns are changing a lot, then you need to rerun the setup. Okay?
But isn't it true that many of these data come in partitions? So you don't have to join the partitions. Suppose you can do independent compression for different partitions, even though represent the same set of data.
Yes.
The same.
Actually, you are right. The idea again was in a database setup where you have already the columns. To be honest, we are focusing more on the archiving part. So there is no much of updates of the data. So you have the data and you want to store them in a specific way. But the huge value is this 56%. Okay, because you have archiving data, you don't need any updates. So this works very good on the archiving data. On the updating part, yes, we can do different techniques, but again, we are at the first step. Okay, it's not finished yet. Yeah. Any other questions, Daniel? Six. Yeah.
So
okay.
the idea of, getting rid of testing all combinations is how like Amazon or Oracle, whatever, instead of doing query optimization, they have this huge back catalog of what the best plan was then, and they just try to match it to that.
So this is a good common question. I have talked with a lot of people in the industry. For example, Snowflake. Snowflake is using something similar, but not at this level. So they are using a predefined compression scheme for each type of data. For example, if it's an integer, let's use GIF. If it's a string, use something else. So they are using this in a, let's call it in a blind way. This is a column, this is a type, this is a compression. That's all. We are doing something different. We are putting different columns together, and then we are identifying the best compression scheme. Now, the difficulty in this is to identify the parameters. You need the number of clusters, you need to find the best compression scheme, you need to identify the features that you are going to use. So this is our contribution in that specific part. But yeah, fine.
And so that kind of gets at like a second question I had, which was, parquet and working things like this. One of the like techniques that people were exploring early on was that each of these partitions can use a different compression scheme.
Correct.
And they try to use that to, push their storage sort of minimization. How does that compare to, so like that's at a different level, right? It's file partitions versus columns. But did you compare how this approach goes to like the, when you apply all the same tricks at the file?
Okay, very good question. I didn't compare that, but other people compare that. So this is good enough. So there is different databases that are trying to do something similar. For example, timescale, timescale. They are taking the columns and they are trying to find the best conversion. But this is only on the type. So again, it's better than the partitioning, the conversion of each partition, because they're taking the whole column. And they have shown that in a relational database, PostgreSQL with Toast. So yes, there is work that is showing that there is a bigger potential, let's say, to compress the data. So yeah, very, very, very good question. Okay, any other questions?
Are you gonna give us the insight, or is that like the
I will give you
secret sauce?
I will give you a small hint at the end. A small hint.
Oh, okay.
Okay. Yeah.
Did you compare the storage performance against like what's like, for example,
Yes, but I don't have the results. But I know the results. We are pretty okay. This is the only thing that I have.
difference? Because
So for the actual part, I think is 7%. Okay. So you are asking very good questions.
In comparison to what?
The snowflake approach.
one,
Yeah.
Just one clarification. Since you're making columns here, so this is only applicable for relational or structural data. Or
Right now we're focusing on that.
only on the
Okay.
relational?
Actually, we are focusing on column storage, but then in a row store. So relational database with rows, with tables, but actually we're focusing on storing the columns.
But
Okay.
this leads back to also the paquet.
Yeah. We already, Vasily, you want to collaborate? We have a lot of work to do. Okay. So, we already discussed this. I'm going to, yeah, we have time. So I'm going to move to the data decay part of this talk, and I think, and then I have some questions. This started during my PhD. We continue a collaboration here at PIT, and we want to still collaborate in improving these things. And we're going to discuss it here. Okay, so we have the compression, and we have different ways to reduce the data. We have sampling, we have aggregation, we have reductions, we have synopsis or sketches, and then we have data conversion. And we already said that this is very important in our case, in our product, in Compass, because it's working in a way that we are not losing anything. It's lossless. Okay? So the problem is that, as we said before, we're getting the data, storing the data, storing the data, and then it's going to grow the data storage, the data stored in the system. So we want a way to remove the actual data. So the way to remove the data is the data prescription. It's a term that we devised during my PhD. The idea is that we are going to remove the data and use a machine learning model in order to recover back the data. Just to show you the idea, I'm pretty sure that you know how machine learning algorithms works. You have training data set, you are training the model, you have a testing part, you are testing the model, and then you can do predictions. Okay. In our case, the data prediction part, we are training the model in the same way. We can test the model, and instead of doing the predictions, we can predict the past. So we call it post prediction. Okay. So we can predict the past, which means with a model, we can recover data that was deleted from the system. Of course, there is this issue with the accuracy that we're going to discuss. So an example, let's say you have this table. I'm pretty sure that Brian, you know this, right?
Yeah, I mean, originally it was Anna.
Yeah, correct. So you have a huge table, a lot of values, and you want to delete some of the data. So what you need to do is to have a recovery table, a way to find out what data you need to recover, and also a model for each one of the features that you have in the system. Okay. So if you want to get back, for example, the height, you can say I have 162 for ID and weight, and give me back the height. So you're going to get back the height with some accuracy. Okay. So again, the whole idea is to have two algorithms, a construction algorithm that is taking the data, creating a model, and then store the model, remove the data. Okay, so now we have the model that we can use to recover the actual data. In order to recover it, we need to load back the model, ask the model with specific information, and get back the data. Okay. So we wanted to see how this can improve the storage space. This was done during my PhD thesis. So it was the first version. And let's discuss it. So we have the raw, absolutely zero application of anything of data. But let's go to the question. Yep. Yes. You did it? Yeah.
Yeah, so maybe in the future, so and the P will be removed totally, and you will have the P1, P2,
Correct. So in our case, because we wanted to be a system-based function, let's say, we wanted to allow the system to choose how much data we want to delete. In this case, we could remove the whole thing and have only B and the recovery tables. Yeah.
and P will be stored in the.
And then this. Yes, correct. So instead of storing the data, we're going to keep the model in the NVC and then load it to recover the data. So we want to compare it again, the standard techniques. We have nothing was applied to the data, the conversion, some sampling, randomly choose only one record instead of storing everything, and our operator, the data restriction operator. We wanted to focus again on the storage, but in this case we have accuracy. So we have this normalized root mean square error in order to understand what accuracy can be achieved. We have the same data set as before, the telecommunication operator. And let's skip this and go to the experiments. Okay, so the good thing is that we are saving space. We're removing data, so yes, it makes sense, right? We're removing a lot of space, but there is a problem. The problem is that we had a normalized root mean square error of almost 50%, but again, there was potential. there is some data that are giving very good results. So we said at the second step that we can achieve a better accuracy. So let me go to the next part about this accuracy. We said we want to guarantee this accuracy. For this was a collaboration with Anna, Ryan, Adaptis, the paper Adaptis, that we can achieve predefined accuracy. Okay, so yes, we're getting the data. We want to apply data restriction. We can do some outlier detection with some clustering, and this will allow us a specific value of accuracy. Of course, if we cannot achieve it, we need to go back and redo the work. We're going to see it in action now. So let's go to the actual technique. So let's say we have this table. We have ID, height, weight, and we want to remove some of the data. So the first thing that we are going to do is to remove the anomalies, figure out what are these rows that are not matching with the rest, put them in the outlier table. The next thing is to figure out what values are similar and put them in different clusters. And then we can apply the data decay. If we do that, we can only achieve 47% of the 95% requirement of accuracy. So this is not enough. We cannot do only an outlier detection and then a clustering, and we're not going to get the correct accuracy. So what we wanted to do is to have this pipeline, and if there is the accuracy that we want to achieve was not achieved, we want to go back and remove more data. So put this higher prediction error data to the outlier tables. So we move this to the outlier table, and then we're going to achieve what we are looking for. So which means we can achieve a reduction of data. So remember that we are removing some of the columns, and then we are recovering back the columns. So what we do is to have an outlier table, we have a recovery table, and then we can recover back the data. Okay? So remember that let's give you the full picture. Sorry about that. Remember that we have this huge table, right? We have many features. In the example are only 5, but we have many columns. So what we want to do is to have a recovery table to recover the data, but also models for each one of the columns. Okay. So the problem is the accuracy. Okay. And we managed to achieve that by this pipeline, which allow us to adjust the numbers, the number of the pipeline records. Okay, if something is not good enough, let's put it on the outlier table. Now, just for completeness, the outlier table is a table that is going to be stored in a raw format. Okay, no decay applied, no compression applied. So we are going just to have the values as before. Okay, so
still compressive with the traditional way.
yeah, or we have with our previous group, right? Yeah, but we didn't do that in this case. So at this point, we have the recovery table. For example, in this case, we have removed only one column. Okay, we have ID height. We don't have the weight. but we can use the models that we store, and in combination with the outlier table, we can recover the whole table. Okay? So another question is about how many columns we can delete from the system, okay, or how many models we can create in order to get back the table with a predefined accuracy. Okay. So in this case, for example, we can see that the age can predict these columns. Yeah. I'm going to. So one of the best results, I'm going to go over it very quickly, is that API can estimate age and height with 82.59% of the original table, okay, which is a very good, again, potential in this scenario. One of the most important things to discuss or to know is that this only works on a huge amount of data. Okay, if the data set is very small, then the model is going to be bigger than the actual data. So you need to reach a specific point of the actual data set in order to have better efficiency in the storage. Okay. So let's go to the conclusions, the future work. We saw that there is a ton of potential in the data storage part. We built Spate. We saw that only with the simple conversion, you can get a lot. Then we are working with AMT, of course, on the construction pipeline. We have a ton of work to do, Ryan. And then we saw how an intelligent compression or a smart compression, let's say, can achieve better results. And the hint that I was talking about earlier in our knowledge base is a random forest decision tree. So yes, we are testing everything, we are storing everything, and we can create a model that can give us back the best compression scheme. Okay. So the last thing, we want to build these tools. We are doing a lot of research with different universities. And at the end of the day, we want to enable organizations to find the needles in a field of cases. So I want to give some credits to the teams back at the University of Cyprus. We are still collaborating. And of course, the AMT lab. This is Brian. Yeah, see. And Banos, of course. So thank you so much. If you have any questions, please feel.
So we have a few minutes for questions.
Yeah.
So one of the things that's like a user-defined parameter is the accuracy threshold for those models. Do you look at all like, you know, what would be great is if you can decay one of the columns that can predict another column, so you can decay that one, and you kind of get this cascading effect. Is there a sense of the threshold on the secondary, third, like that cascading error, I guess, if that makes sense?
Actually, no. It's a comment that is giving me food for thought. And actually, now that you are saying this, I thought that maybe the outliers table can be decay as well. And because this is the anomalies, maybe the anomalies have something in common. So maybe we can do something about it. I'm not sure. We may explore it.
I think what I'm going to ask you is also for thought. So, what's happening under, like more closer to the storage layer. So for example, SSDs, if you write too often, we bought, about the flooding, we have to buy new servers, so we look at the new storage technology, and they still sell the old style hard drives, but now there are different SSDs based on how many rewrites you can do on them. So there may be an additional trade-off to, if you delete something, maybe it's not worth, deleting and overwriting because you have a certain type of disk versus, just letting it be there and, so that's the one thing. And also along the same lines of finding this disk on disk, then being sequential versus things with lots of holes that you plug in other stuff in, or you have to, I don't know how many of you know about defragmenting hard disk drives, something that we used to do way back when. But there is all these other lower level storage that I don't, so I don't know how, if you've looked into that, if they are orthogonal or if there's some co-evolution that you have in the future.
For sure. So this is the only thing that, we can do a lot of stuff with different tiers of architecture. We had a small exploration. There we have the SSDs, we have the hard disk, what to store in one level, what to store in another level. But I think one of the most interesting directions of this work is the sustainability part. That we saw that there is potential there as well. So you can reduce the energy for the disk because you have less space, you have less I/O, so you can explore different directions. But yeah, the lifespan of the disk is a huge subject as well.
I guess since you mentioned sustainability, another one also is cost. Depending if these disks are on the cloud, then they come with different costs.
Yes.
And different SLAs, obviously.
And actually, you check the plan, especially from Microsoft, you have the hot storage, the cold storage, and you have the archiving that you store the data, but the data are not accessible. Which, yeah.
Again, going back to this question, the target is not the live data that they are operational on the daily that they keep updated all the time. So because you are looking into this archival data,
Correct.
And the dark data.
First, this is really interesting, and I think he is the best person to talk about cost, right? Because with a name like that,
No, it's the
cost comes.
it's the chain of the cafes, Costa coffee. That's it.
But I was going to say something that I think that's what you said when Vassilis asked his question. Did you apply the same approach to the outlier table? How big is the outlier table? Because maybe the outliers that you pick from the original data form a table that has a model, and maybe you can pick the outlier table out of it and then use your previous scheme or just use. So that was one comment. The question is, how big is the outlier table that you use?
It depends.
In comparison to?
It depends. The worst case scenario is going to be the whole table, the original.
But you saw examples that it's the whole table?
No.
Okay, so worst case is the whole table. Best case is zero outliers. Okay, so now we establish the boundaries. More experience.
And the best case, it's nothing.
Yes.
But if it was its own model, wouldn't it be a cluster?
But so I'm asking, so because you said in the beginning, I said, are you gonna tell us some insights or is it secret?
Hints. Okay. Only for the compass part.
So let us provide some of these insights. So usually the outlier table is in the worst case that we saw was one service. It's much smaller in general. The second, you cannot make it clusters. We thought about that. That's why I make this hint. That will be compressed. So that is a table that provides 100% accuracy because you cannot do better than that. And I can, because it's small also, it can do efficient compression even with this 4 or in some cases 17% that with the time series, it was not only 7, I thought it was 17. So that is basically the.
Okay.
So
I had another question. Your motivating example was health. Your test was telco. There is a cost for telco. Maybe the cost is lower, but for the health, the cost is higher of misprediction. Right?
Yeah.
Okay, so fine. You have almost 100%. That means that that person has diabetes.
Correct.
So,
Sorry, you're right.
sorry,
Absolutely.
we operated on the wrong person.
Absolutely right. Yeah. In this case, we use that specific data set, but yeah.
You're an insurance company.
But then you may get killed.
You're right. I think that the question is about the 95% accuracy because that
no,
is
it's it goes beyond,
right?
beyond that.
Yeah.
Actually, I think the way that sometimes I envision these things is we have this beautiful concept of conditioning. There are some data that they have to be preserved to 100%. Those become ineligible for being compressed in either form or whatever. So now we're saying that the majority of the other data, which are commonly used and we keep having them, and that's why I mentioned also now the data, are there lying in the basement. No one knows what they are, and they just growing into these Blu-rays, whatever we're going to call them, which needs to be handled. Either you need to make a decision, delete them, simulate failure or flooding, or do something about it that can be turned into some useful or data value, produce value. So this is the target data that we also want to include rather than thinking always in the operational, the fresh data that everybody else say, oh, this is the fresh data, let me show you.
But you also were mentioning that there's some aggregation, so you may not be able to ask the same sort of questions to the data from 2014 than 2017. So the models don't have to cover all the data.
So the model should cover all the data. The first version that I showed in the decaying of the year was the first idea. Let's delete the data from the beginning, for example. So you have only the highlights. But that was the first idea of the decay. The other more sophisticated versions are looking at the data, creating the models for all the data. So you can recover everything that you want and even use the model to predict data as well.
So the question that you have just asked, I asked him during his defense. I asked him, how do you decide what the level of aggregation, what queries you are doing? Because that, if you want to do that in a user transparent fashion without any intervention, then you cannot do that. So it basically is an application dependent. And the following up question was, can I use machine learning to predict what will be the common queries and so on based on experience in order to do this aggregation? And he answered that question better than now.
Could you, like, for the thing the model gets correct, can you just use a model, but if it gets it wrong, can you hard code the correct value?
Yeah, this is the idea of the outlier table. So if it's far off, let's put the table as it is in the outlier table. Yeah.
I will give Felix the last question.
In the results you showed 100% accuracy for the decay. But like, are you always shooting for 100%? I'm just having a little bit of
So yeah.
Using LSTM, I have the feeling that it's just overfitting to your data, and it only works if you have a lot of data. And then maybe just doing compression instead of decay is gonna have more or less the same memory cost. Because right now you're just saying you're using a big model, and then you just have all these duplicate entries, and like perfectly fits it. But so if you just compress it, you might have the exact same.
Yeah. So if you want, you are absolutely right. If you want 100% accuracy, you need to do something else. Okay. If you want to trade some accuracy for space, you need to find the golden parameter in order to get the, for example, the 95% accuracy. Okay. So you're trading, trading space for accuracy.
Okay, yeah, I just wasn't sure.
Yeah, so it's 100% for the accuracy we were going, which was 95%. We tested a wide range of accuracies to see like the trade-off of like, if I sacrifice this much accuracy, does it actually save me a lot of space? And it was I forget what the actual name is, but it sort of flattened out the more accuracy you gave up. So we found that like after 98%, if you went below that, it wasn't really worth it to do that. But for that paper specifically, 100% was, we said 95%, so no more error than 5%. Anything that was more than that, like the 10%, was stored separately in the outlier table.
So it's 100% of 95%.
Yes.
Correct.
Now, I will say lately, because you mentioned the LCM, we have tried smaller models because we thought the same thing. This is overkill and large, and we originally based it off of the telco data. It makes a massive difference. So if you do a smaller model, it basically moves that inflection point way farther left. So you start saving space earlier on smaller data sets, and it basically lets you get more clusters because you're not paying as much cost for the model itself. And that in turn gives you a lot better savings. So like here it was like 56 or something. I think we were happy, or 85% of it. And now measuring the cost of the model, the outlier table, the recovery stuff, we've gotten some data sets down to like 8% of the original data size with like 99 point something % accuracy.
So it's pretty good.
So it makes a difference.
Thank you. Apologies for keeping you longer, but it was an interesting discussion. Thank you again, Constantinos.
There is.
If you want.
She did.
Careful what you say, recording is still on. Yeah, you can say and from there.
6 minutes.